So after we have understood about what Fourier transform actually is, let us now take a numerical example to really work out the nuances of Fourier transform and what does the discrete Fourier transform formula tell us. So let us once try to reminisce about the formula. So it is said that if I have a set of variables xk, let's say is the concentration, and the concentration is a function of time. Okay, so x actually denotes the concentration and it's a function of time. So let us say in our concentration versus time profile, so time and concentration, I have at time 0, 2, 4, 6. So let's say I have these many points. Okay, I'm not going for all the points, of course, but let's say I have only these 4 points at these different times, and I have the concentration, let's say 1.0, then 0.8, or let's really go to whole numbers just to make life easy. So let's say this was 10, this was 8, this was 5, and this is 2. Okay, let's say these are the values. Now in order to go from this data, if I want to do discrete Fourier transform to get this capital Xk, then what is my capital Xk? So capital Xk is equal to summation n goes from 0 to capital N minus 1 xn e to the power minus 2 pi I over n, this is small n, and this is k. Okay, so these are the values. So what is capital N here? It's a number of data points. So we can call this as C0, C1, C2 and C3, or keeping with x, you can also decide to call it x0. So let us say these concentrations are my original data x0, x1, x2 and x3, and from there I want to do a discrete Fourier transform. They are discrete because the times are at discrete time points, their values at discrete times. And what is delta t here? Delta t in this case is 2. So for these formula, this delta t is actually not required. We are just randomly giving them not randomly, we are just giving them sequentially x0, 1, 2, 3 numbers, and we could have several more, x4, x4, x6. Let's say we have these 4 points. Now what we are going to do, we are going to find each one. So what is x of 0? Capital X of 0 is equal to summation, right? Summation n goes from 0 to, what is n here? Capital N here is, there are 4 points, so it's 4. In this case, 0 to 3 xn e to the power minus 2 pi I. What is k here? K is 0 over n. So since this exponent in this case is 1, it's simply a sum of the different values of xn. So it is 10 plus 8 plus 5 plus 2. So 18, 20, 25. So that is my x0. What is my x1? That will be a little more complicated. So that is n goes from 0 to 3 xn, small xn, e to the power minus 2 pi I. Now k is 1 over capital N is, n is 4, right? So what we have here is 4. So what we have, it's equal to, and then we have into n, small n is there, of course, this small n. The k is 1 here, which we are getting from, this is my k with xk, and the n is coming from the summation. So this n is actually coming from the summation over here, right? This n and this n is the same. So now what are the, so n will start from 0. So x0 e to the power minus 2 pi I over 4. So that is, I can simply write pi by 2, I pi by 2 into n is 0, plus x1 e to the power minus I pi by 2 into 1, plus x2 e to the power minus I pi by 2 into 2, plus x3 e to the power minus I pi 3 by 2, right? So what do we have here? That is equal to x0. What is the value of x0? 10 e to the power, so this exponential is 1, so 10 plus x1 is 8 e to the power minus I pi by 2. So that is cos pi by 2. What is cos pi by 2 is 0 minus I sin pi by 2. Sin pi by 2 is 1. So 1 into I plus x2. What is x2? 5 into e to the power minus I pi. So cos of pi is minus 1 and sin of pi is 0 plus x3, and here we have what is x3 is 2 e to the power minus 3 pi by 2. So what is 3 pi by 2? Cos of 3 pi by 2 is again 0, and sine of 3 pi by 2 is sine cos. So that is positive, so that is minus sine pi by 2, that is 1. So that will give us plus 1, 3 pi by 2. So that will give us 10 minus 8i minus 5 plus 2i. So that is equal to 5 minus 6i. So similarly we can find out what is x2. That is equal to x0 is 10 e to the power, here it will be e to the power minus 2 pi I 2 by 4 into n. So it's just pi I into n. So e to the power minus pi I into 0 plus 8 e to the power minus pi I plus 5 e to the power minus 2 pi I plus 6 e to the power minus 3 pi I. So that is giving us 10, and pi we know is cos of pi is 1 and sin of pi is 0. So for all these cases, pi, minus pi, 2 pi and minus 3 pi, what we are getting is only cos. So that is 1 plus 8 plus 5 plus 6. So that is again the same value as we had before, that is 25. Now what do we have for x3? That is 10. Here the exponent is e to the power minus pi I 3 pi I by 2 into n, right? So that is 10 again e to the power 0 plus 8 e to the power minus 3 pi I by 2 plus 5 e to the power minus 3 pi I plus 6 e to the power minus, so this is 3 is a 9 pi by 2i. So this is basically giving us what is it giving us? 10 plus 8, oh, just a minute, I'm sorry, this is minus 1, so I made a mistake here. Cos of minus pi is negative, cos of 2 pi is positive, cos of 3 pi is negative. So 15 minus 14, this is actually just 1. I made a mistake, okay, I just missed it. So 8 into 3 pi I by 2 is what? It is just 1, 0 plus I Now 5 into, again cos is 0. Now 3 pi, again cos is positive and sine is 0. So what is cos? 3 pi. So just equal to just pi. So that is minus 1 plus 6 into, again 9 pi. So 9 by 2 is basically 4 pi plus pi by 2. So 4 pi is equal to 0, same as 0. So pi by 2, sine pi by 2 is minus pi. Right? So that is 1. Why did I get these lines? I don't know. Sorry. So what do we have here? We have here simply 10 plus 8i minus 5 minus 6i. So that is equal to 5 plus 2i. So these are my 4 values. So we have what did we have before and what do we have now? We had x1, x2, x3 and x4. Oh, sorry, x0, x1. x0 was 10, 8, 5, 2. And now we have the Fourier transform values, capital X0, x1, x2 and x3. So what are these values? Capital X0 we got as 25. Just the sum of all the values. Capital X1 was 5 minus 6i. X2 is 1 and x3 is 5 plus 2i. So these are the different values that we have got. So from here, what does this actually mean now? Okay, that we have got this Fourier transform values of these values. So what does it mean? It means basically, so for example, this x2 equal to 1. What does that mean? So that means we can find the amplitude of frequency. So what is the amplitude of the frequency? What is the frequency? The frequency is P is equal to 2 pi by n delta t into the small k here. Okay, so what is k here? It is 2. So 2 pi, what was n? Was 4. Delta t in this case is 2 as we have taken. So here the delta t is important. How many time differences we have? Into k. So k here is the second one. So it is 2. So that is pi by 2. So the frequency pi by 2, the amplitude is 1. Okay. So when the frequency is pi by 2, the amplitude is 1. What about x1 is equal to 5 minus 6i? Now how can I say that 5 minus 6i is an amplitude? That is not really possible, right? Like it's complex. So how do I find out the amplitude here? We can tell the amount of the amplitude. What do you do when you have a complex variable like this? You can say that the amplitude of this is psi I star psi I square root, right? Just like we do for our wave functions. We find the probability, right? So this one is psi I star psi I. So that is 5 minus 6i into 5 plus 6i. So that is 25 plus 36 square root. So that is square root of 71 is basically our amplitude for a frequency of, what is the frequency? Here P, let's call this P2, then this is P1. What is P1 here? 2 pi over n, that is 4. Delta t is 2 and k here is 2. No, k here is 1. We are looking at the kth. So you understand, right? All these numbers are the same. This number here I'm calling it P1 and I'm multiplying it with 1. So that gives us the frequency. And what is the frequency? The frequency is pi over 4. So for a frequency of pi over 4, the amplitude is square root of 71. So what is the value of square root of 71? Is square root 71 square root of 5. That is around 8.42. Okay. So like this, in this way we can actually find the amplitude of the different frequency values. Okay. So this is what the discrete Fourier transform actually does. But suppose we are looking at something like a UV visible spectra. So when I am looking at a UV visible spectra, what do? We take the different wavelengths, and this is the output, right? The output looks like something like this, where we have the wavelength here and we have the intensity here. Do you know how it's done? Yes, we change the wavelength of the light that is incident on a cuvette containing the solution, right, of the chemical that there is. So when a particular wavelength goes through it, if that is emitted, if that is not absorbed, then it will be high, and if it's absorbed, then it will be low, and so on and so forth. So that way we can say what has been absorbed and what has not been. But suppose in this case I don't have a monochromator. That means I have a light that is basically giving off your entire, I have a light that is giving off the entire series of wavelength. Okay, I don't have a light that gives only one wavelength at a time. So in the UV visible we are going from 200 nanometer to 400 nanometers, right? So instead of taking each of these, so 200, 201 and so on and so forth, I don't have all of these. I have a light that's giving off something that is a mixture of all these. So the UV lamp under which you see the slides, for example, so it's giving off all the wavelengths. In that case, how can I find out the spectra? Is it even possible for me? So what is done here is, first we put this light through the cuvette and we get a signal. Next we put, so we get just one intensity, so some one data point, right? So we get an x0. Then I put a mirror, we put a mirror in front of it so that some of the wavelengths are cut off, let's say, and then I get a x1. So similarly I will get a whole range of data points up to xn or capital N minus 1. Okay, so when I have this whole range of data points, then these can be taken and Fourier transform done on it to see that which frequency is actually there or not there. Just like in the case of our smoothie, we will find out which frequency is there or not there. Similar thing is more, you will understand better when we talk about emission spectra of a star. You know, you are just getting at a particular time all the values. You know, at a different time you are getting all the values of whatever light intensity is falling on it, right? At a time we are just getting the intensities, and we can take that value. So we are taking the intensity as a function of time, and then we can just break it into its Fourier transform xt. So that way we will be able to say that the light emitted, so what are the different frequencies it has, and using that kind of data we will be able to generate a beautiful emission spectra, right? So an emission spectra like this can be generated. So this is how you can read up more on the FTIR. But basically for the Fortran part that we are using, what we are doing basically, I'm not going to pull out up. So what we are going to do, we are just saying that given a set of data xk, we can go from, which is called, if x is a function of time, we are going from the time domain to the frequency domain. We are going to capital xk. These k's are just dummy variables, 0, 1, 2, 3, 4. Just say that how many discrete points we have. Okay, it has nothing to do with the time 0, time 1, time 2. Time could be actually t equal to 0. For example, in this case, at t equal to 0 we had x0, at t equal to 2 we had x1. So delta t was 2. We can have delta t of 0.01. In that case, this would be, I'm just using a different color. This could be time at t 0.0, 0.01, 0.02, 0.03, and still this would be our x0, x1, x2, x3. So 0, 1, 2, 3 are just the counters k to tell us how many data points there are. Okay, so if I have xk and I can go to capital Xk, how? Capital Xk is equal to summation n goes from 0 to capital N minus 1 when you have a total of capital N values, xn e to the power minus 2 pi I over capital N k into n. Okay, so this k is the same as this k. This small n is just this counter small n, and this capital N is the total number of terms, that the data that we have. Again, what we had discussed earlier, that suppose now I have these different parts. How can I go from there to the original? Can I go from this capital Xk to small xk? Yes, we can do so by inverse Fourier transform, that is given by 1 over n. So that's n is the total number of data points again. N goes from 0 to 1, xn, this is capital Xn e to the power 2 pi I over capital N kn. So you can see it's just the same. The only difference here is basically this minus is there, here it's not there, and this 1 over n is here. We are basically dividing the whole term into this 1 over n. Okay, so we are summing it up and then we are dividing it into the we are taking average basically, kind of, okay, over all the n values. So this, by this method we will be able to get back into the time domain. So even if this is not time, it is often called the time domain. In the case of wavelength, right, we can have a function of wavelength, that's not really time, but in principle, since it was started with this time and frequency, the first one is called the time domain, the second is called the frequency domain, and we can again get back to the time domain. Many times it helps us actually get more beautiful data than it actually was to start with. Okay, so this is something you can try now to do the examples that we have done. And in the problem that if I go to the problems given on the 1st of May, so you will be able to see that we have asked to find the Fourier transform of e to the power x between 0 and 10. So what is the delta x here? Okay, so this is e to the power x can be said to be your f of k, right? So I can have k, how many terms? You want to have 100 values, you want to have 1000 values. If you want to have 1000 values, then delta x is 0. So if I have delta x as 1, then I will have 10 values. If I have delta x as 0.1, then I'll have 100 values. If I have delta x equal to 0.01, I'll have 1000 values. Then if k is equal to 1000, then I will have f of 0, f of 1, f of 2, f of 3, and what that is equal to e to the power. So basically my delta x in this case is 0.01. So e to the power 0, this is e to the power 0.01, e to the power 0.02, e to the power 0.03, and so on and so forth, where f 1000 is equal to e to the power 0. Basically e to the power 10.0. Okay, you got it now? So here in this case you have to choose a delta x by yourself. Here x actually, in this case x was a function of t. Here fk is a function of basically x. So basically we are x is now changing as a t, x is just a variable, so you can say the delta t, how much time step you are taking. So you can go from the, will be the time domain. If this is basically your time domain by definition of DFT, you can go from here to the frequency domain. So you can go to Z0, G1, or I can just want to write it as capital, just like we did. So you can go do the Fourier transform and find capital F0, F1, F2, F3, and so on and so forth. So that's the first question. The second question is, we have of f of x is equal to cos of 2 pi 3x e to the power minus pi x square. Okay, and the range is given as minus 2 to plus 2. So this x goes from minus 2 to plus 2. So you can again divide it into different parts, and the first value of x will be minus 2 and the last value of x will be 2. You have to decide how many data points you want to put. You don't put we generally don't, if I want to do it manually, of course these are the values I'm going to choose. But since I'm not going to do it manually, I will never get a perfect value in this way, right? So I'm going to do it using a computer, and I can find all the different values of the Fourier transform value, right? What else do I have? I have, oh, here we also said something. We said use the following functions and look at the form of the graph. So the function e to the power minus 2 pi I 3x and e to the power minus 2 pi I 5x. So we are saying that instead of using e to the power minus 2 pi I n k into x, right? We said that instead of using that, calculate the DFT using these two functions and then see what is happening, okay? Whether it's changing, whether it's not changing, what is happening to it, just look at that. And the last question is write a program to calculate the autocorrelation of, oh no, this one, the question 2. So this is interesting. Use the discrete Fourier transform. So you have been given a real data to generate the UV absorption spectra from the given data files in this beta SICA R dot dat, and which has the real and imaginary part. So here the data we have, okay, x is now equal to a plus ib. So you take both this a plus ib as x. X is a function of time. So you have x0, x1, x2, etc. You have a plus ib, both the components, and then you are going to find capital X0, which will be, so let me call 0 a0 plus ib, a1 plus ib1, a2 plus ib2, and so on and so forth. So when you are doing the summation, you have a k, oh it's not k, sorry, an. So xk, what is xk? Xk is equal to summation n goes from 0 to n minus 1 a n I b n e to the power minus 2 pi I k n over capital N. So you have to find out what is the capital N from the data points. You can calculate it as you read the file using that way where I said that how to reach the end of the file. You don't open the file and look at the data. That's something you have got to learn. How to say when you are using a do while loop, how to say that you have reached the end of the file. I have explained that in a class and you should look it up otherwise. And then you have yes, this k is the same as this k, and you have the n as a part of the, so here you already have because it's a real and imaginary part, you have the real and imaginary part of both, and here also you have cos of this value plus I sine of this value. So you have to basically save it as, so here you have a plus ib, and here you have c plus id kind of a thing, right? This exponential. So here what do we then have? AC plus, so AC minus BD, right? That is the real part. The other day I discussed with you, right? So here in these cases, when you are doing this Fourier transform, you're going to have f0 is equal to summation small n goes from 0 to n minus 1 f0 e to the power, so cos of 2 pi I k n by capital N plus sine of, so capital N here is 1000, not k is 1000, capital N we are deciding, so 2 pi I k n by 1000, right? I sine of, so you have the real part f into this, and you have the imaginary part fk into this. So n is 0 of course. So if I decide to write this as a general formula, I'm just, so fk is equal to kn fk. So then you can find out f0, f1, f2, etc. In this way. So you have a real part, so you are going to save it into a real part, and you are saving it into an imaginary part. So if I want to plot as a function of k, so k, real part of f of k and imaginary part of f of k. So you can just save it as two different columns, otherwise you are not supposed to write, right? So k will go from 0, 1, 2, 3, 4 up to 1000. That will be your output file. In this case, what is your real part? This is your real part, and what is your imaginary part? Plus I of BC minus AD, right? BC plus AD. So this is your imaginary part here, because you have I sign of something, you have C plus ID, you have A plus IB. So your real part is also complicated, your imaginary part is also complicated. So that's how you do this program. And then you can do the inverse Fourier transform to again see what you get and what you don't. Okay, so this much I wanted to discuss with you.